Hey, let me play you a scale. That was a scale derived from Overtones of the Harmonic Series, and if it sounded a little out to you, maybe this one will sound more familiar. Here's another one. This one's kind of wacky. And this one is, without a doubt, the most common scale in modern times. Okay, so there are all kinds of scales. And all the scales we just heard, except for maybe the wacky one, could make some claim to being the most natural or most basic. But of course, there's no single most natural scale, and there's no scale which is most harmonious. In fact, any method of constructing a scale necessitates some compromise in terms of harmony or being in tune, because math. Math has a lot to say about questions that arise when we think about frequency and pitch and scales, which are collections of notes, and tunings, which are how precisely you tune those notes. Now, I want to say at the start that the question of what sounds good to us or interesting is predominantly influenced by culture and history, and it's very subjective. But math can shed a lot of light on these questions, and it can help us understand and appreciate the rich variety of scales and musical traditions that have existed through time and through space. Here's a quote Georg Cantor said, "The essence of mathematics lies in its freedom." So once you understand the mathematics, you can create your own scales if you want. So let's dive in. I don't want to assume a lot of familiarity with music theory, but this whole exploration is going to go a lot smoother if we can just use some terminology that's modern and common. This here is well, you know what it is. The 7 white keys make up what's now called a C major scale. C is called the root note. This key here is also a C. The white and black keys together constitute the 12-tone chromatic scale. The interval from one key to the next is called a semitone, and 2 semitones make up you guessed it, whole tone. Modern pianos are equally tempered, so the ratio of one frequency to one a semitone below is 2 to the power of 1/12. We'll learn more about this in a bit. The interval from this note to this note is called a perfect octave. From this to this, a perfect fifth, and from this to this, a perfect fourth. These names will make sense later. This interval is called a major third. It's 4 semitones. This is also a third, but it's a minor third because it's only 3 semitones. We also have intervals of major second, major sixth, major seventh, etc. When talking about scales and tunings, there's a useful unit called a cent. A equally tempered semitone is equal to 100 cents. Since a semitone corresponds to a ratio of 2 to the 1/12, a single cent corresponds to a ratio of 2 to the power of 1 over 1200. For most humans, it seems, the threshold for differentiation of pitches seems to be around 5 cents. So most people can perceive that these two tones are different, but can't perceive that these two tones are different. This is an important point that will come up again later. We can't perceive really small changes in pitch. Okay, why 7 notes in the major scale? Why 12 notes in the chromatic scale? Why not 11 or 19 or 53? What's up with the names perfect fourth, perfect fifth? Why are octaves such a big deal? The answers to these questions aren't purely cultural or historic, although they certainly have a big role to play. Math has a lot to say about it as well. In order to learn what the math has to say about it, we should probably spend a minute and briefly discuss the physics of sound waves. When an object like a drum head or a tight string vibrates, it moves the air around it. Imagine these black lines represent such an object. As the object moves to the right, it compresses the air immediately next to it into a small high-pressure region. This high-pressure region will then push against the relatively low-pressure region to the right of it, and a chain reaction ensues. The vibrating object causes little pockets of air to oscillate, and the variations in the air pressure to propagate away from the source. This is called a sound wave. You can see that the air pressure of, say, this region goes up and down, as represented by this dot. If we plot the change in pressure over time, we get a sine wave. How fast the object vibrates will determine how fast these little pockets of air move back and forth. If, for example, they go back and forth 130 times in 1 second, we would say that the sound wave has a frequency of 130 hertz. The wavelength is the distance from one little pocket of air to the next, one high-pressure region to the next high-pressure region, or low pressure. And wavelength and frequency are inversely proportional. So, for example, doubling the frequency halves the wavelength. If the frequency of the wave is somewhere between 20 Hz and 15,000 Hz, and there's a functioning human ear around, these tiny disturbances in the air pressure will disturb the inner mechanisms of the ear, which in turn will send a signal to the brain that is interpreted as sound. If the frequency of a sound wave is doubled, it is exceedingly common for the human brain to interpret that new frequency as the same note. The interval from the lower to the higher doubled frequency is nowadays called an octave. Yes, octa for 8, but that naming has nothing to do with doubling frequency and everything to do with scale construction, as we'll see later. It has long been thought that this perception of octaves is due to the biology of the human ear, although some recent ethnomusicological studies cast some doubt on this. Some argue it may have more to do with the kinds of instruments that we have long played as a species. Instruments made of cylindrical tubes, or instruments made of stretched strings, all of which, when used to produce one fundamental note, in reality produce many, many other notes, higher pitches, and in particular produce many, many octaves naturally and prominently. For example, a tight string will oscillate something like this, producing a tone maybe like this. But it will also oscillate a bit like this, although to a lesser extent. This oscillation by itself produces this tone. This is called the first overtone. Note that the wavelength is halved, so the frequency is doubled. So this is perceived as an octave above the fundamental. But there's more. The string also oscillates a bit like this, and this, and so on. These are called overtones, and the actual motion of the string will be some linear combination of these sine waves, and so the sound produced will be a combination of the fundamental tone and many, many overtones. Some overtones will be louder than others, though none will be as loud as the fundamental, and exactly how loud the many overtones are depends on where the string is plucked, what it's made of, and what the endpoints are attached to. A similar thing happens for sound produced in cylindrical tubes, for example a flute or a clarinet, or in a more sophisticated way by vibrating membranes, like drums. In fact, these overtones are a very large part of what differentiate a pitch played on a piano and that same pitch played on a guitar or violin or saxophone, etc. This is an online applet written by Paul Falstad that allows you to see and hear the effect of adding in these different components. Here we see a simple sine wave represented, and if we click sound, we'll hear the tone. We can decrease the amplitude. We can also add in higher overtones. There we've added in the first overtone, and we hear the octave above. We can add in higher overtones, and generate different tones. The study of this is called Fourier Series, which has a whole host of applications in signal processing, etc. We're not going to get into that in any more detail here. Let's use several of the first overtones to try to create a scale. We'll take advantage of the fact that our ears perceive doubling a frequency or halving a frequency, dividing by 2, as producing the same note in a different octave. That is, for each overtone, let's halve it, divide by 2, as many times as necessary for it to lie between 260 and 520 Hz. So with a fundamental of 260 Hz, the second harmonic, or first overtone, is 520 Hz, with a ratio of 2 to 1 to the fundamental. The third harmonic, or second overtone, is 780 Hz, with a ratio of 3 to 1 to the fundamental, or 3 to 2 to the second harmonic. Rescaling that, we get 780 divided by 2 is 390 Hz. The fourth harmonic, third overtone, is 1040 Hz, ratio of 4 to 1 to the fundamental, or 4 to 3 to the third harmonic. Rescaling, 1040 divided by 2 is 520. That's an octave, which we already have. Fifth harmonic, fourth overtone, 1300 Hz, ratio of 5 to 1 to the fundamental, 5 to 4 to the fourth harmonic. Rescaling, 1300 divided by 4 is 325 hertz. Sixth harmonic, fifth overtone, 1560 hertz with a ratio of 6 to 1 to the fundamental, or 6 to 5 to the fifth harmonic. Rescaling, we get 390 hertz. Seventh harmonic, or sixth overtone, is 1820 hertz, ratio of 7 to 1 to the fundamental, or 7 to 6 to the sixth harmonic. Rescaling gives 445 hertz. Let's see what we have so far by putting these tones in order. If we keep going until we get two more distinct tones, we'll get this. Now that first one, the one with 5 tones, for those of you who know some music theory, that would be a 1, 3, 5, flat 7, but a very flat 7, back to the octave. The second one might sound a little bit like a major scale or a regular normal kind of scale. It's really quite different. If we play them both back to back, we can hear that. With this procedure of adding in higher and higher overtones and then rescaling them so that they come back, the tones come back and sit within an octave, there's really no natural place to stop that. For instance, if we kept going until we had 16 distinct tones, we would get a scale that sounds like this. Now, you might think, well, let's just stop when we get 7 tones, because there's 7 tones in the major scale, or 12 tones, because there's 12 tones in the chromatic scale. But why? Really, this procedure doesn't answer that question of why today we commonly have 7 tones in a major or a minor scale, or 12 tones in a chromatic scale. There's nothing about this procedure that indicates a natural place to stop. Now, a big reason why I'm exploring this is because these overtones occur on stringed instruments, instruments made of cylindrical tubes. These are very, very fundamental to our perception of music and have been for millennia. This sequence of overtones is called the Harmonic Series, and it's really important to note that the earlier harmonics, the ones that occur earlier in the harmonic series, sound louder on the kinds of instruments we play. We perceive them as being very harmonious, and those ones that occur earlier in the harmonic series have smaller denominators in the ratio, 3 to 2, 4 to 3, 5 to 4. The higher you go in the harmonic series, the less prominently those higher harmonics sound on typical instruments, and the less harmonious we perceive them. I don't think that's an accident. We perceive the harmonious intervals to be the ones that occur very, very on in the harmonic series because they sound louder on the kinds of instruments that we have played. At least this is one way of looking at it. And those ratios that occur early in the harmonic series have small denominators, so 3 over 2, 4 over 3, 5 over 4. And this leads to a common perception that our ears prefer intervals where the fractions are simple and the denominators are small. In fact, it's not quite that simple because, as we noticed earlier, we don't really perceive very minor changes in pitch. So you could alter the fraction 3 over 2 very, very slightly and wind up with a fraction which has a really large denominator, and yet nevertheless we don't notice the change in pitch, and we still perceive it as being very harmonious. So there's a certain amount of tolerance there, which we can really use to our benefit in trying to construct scales and tunings which allow for a lot of flexibility.